All right, I'm going to get started now. Um, hopefully the mic will help my voice carry a bit. Hello? Hey. All right. I'm going to start lecture now. Um, so, couple of things. The instructions for installing the virtual machine have been posted. Feel free to stop by office hours, in-person office hours, for help with it if you need it. Um, I've got a deadline this evening, so one of the TAs will be handling my office hours. There'll be a note on my door. It'll be in a room just down the hall. Um, Anything else? There's so there's been one thing I wanted to mention. I've sent a few emails out to small numbers of people about things like getting their Curry accounts and GitHub set up and so on. And I just wanted, so quick question. How many of you don't read your Northeastern email? Okay. In this class, that is one of there's sort of two official ways of communicating to you. One is sending an email, and the other is posting something on Piazza. So if if something is about a homework or lab has been posted on Piazza, I will expect that and is labeled properly, I'll expect that you've seen it. And if I send you an email directly, I don't send emails to the entire class. I will expect that you've seen it. For instance, if one problem this class has from time to time is people borrowing code from each other. If you get an email saying, see me in my office tomorrow about your code, it's not going to help you any to say a few days later, oh, I didn't read my email. So read any emails from me and take action. There won't be many of them. In fact, for most students, there probably won't be any. All right. Today, we're going to continue talking about C programming, and then I'll spend some time talking about shell commands. So I'll start today talking about structures. I'll call them structs because that's the C keyword. I'll probably say structure most of the time. C doesn't have objects. What it has is is what it has is struct, which defines a chunk of memory with certain fields in it. So in Java, you don't know how how the parts of your object get stored in memory. In Python, you have absolutely no idea how they get stored in memory. In C, this is a block of memory that's going to have Um, it has an address because it's in memory. It has a size, and that size is going to be at least as large as the size of as the sum of the sizes of the fields in it. There's, occasionally the compiler will put some gaps in there to make things, if some of the fields are weird sizes. We'll forget about that. There's something else called a union. You may see a description of that somewhere when you're looking at tutorials about structures. It's probably easiest for now to forget that they exist. And there's very few reasons to use them in any reasonable code. Okay, so the code here defines a variable named s of type struct ABC. So once you've declared a structure type, you can use it, until let me back up. There's two ways to yeah. Structures are like functions in that you can either declare them or define them. With a function, you could declare a function that had a certain set of arguments and argument types, and that way the compiler would allow you to use that function. You could call it. There wouldn't be anything to call until you actually defined the function and wrote the code for that function. With structures, you can declare a structure, and the only thing that lets you, you tell the compiler that there exists a structure with this name. that, if I use struct ABC, it's not a typo. All that lets you do is use pointers to that structure. You can't look at the internals of the structure because you don't know what the internals are, but this is enough to, for instance, declare functions that take pointers to that structure. It's probably not enough to actually define those functions because the functions probably want to look inside the structure. The definition tells the compiler what's actually in there. It turns out that one of the things you see in a lot of structures is a pointer to another structure of that type. This works in C. The C compiler can handle this because, in fact, we've already declared the structure by the time we get to here. So we're able to define a pointer to that to a structure of that type. In general, you see, if you're making a binary search tree or something, for instance, or a linked list, you're going to have structures which hold something useful and also have pointers to either the next structure in the linked list or to children in a binary tree or something like that. And because C is a very simple, stupid language, more modern languages have a lot less trouble with this concept of having, a pointer to the same type or a reference to the same type than C does. So in this case, we've declared a local variable. And so this allocates a local variable with a certain size. Typically, on our machines, it's going to be 4 bytes, 16, 8 bytes. So that would make it 28 bytes, because integers are 32 bits on the machines we use, and pointers are 64 bits. So this would allocate a local variable of 28 bytes, and the compiler would know that that is a struct ABC. So we can set the first field in it. We can copy a string into the second field, although the string had better not be longer than 15 bytes because we've got 16 bytes there, and every string in C ends with a 0 byte. That off by 1, that forgetting to account for that final 0 in sizing things is, a recurring fence post error in C programming. Everyone makes it, including me. And then finally, we set, it's not field 3. It's next, and I didn't have any other variables of type struct ABC, so I just set it to point to itself. Now we have a trivial circular list, for instance. I could have also set it to null. This is a distinguished pointer that you can use for any pointer type, and it will, it's typically used to mean something's empty, like the end of a linked list or something. It's not that different from null in Java, and you're guaranteed that if you try to access something at the address null, your program's going to crash. Okay. So the annoying thing about structures in C is that there's two syntaxes for accessing fields. So if you have a structure itself, so something that has a size, bigger than that's not equal to the size of a pointer, that's equal to the size of, the structure with all its fields, then you use the dot operator. If you have a pointer to a structure, you use the arrow operator, just to confuse everything. Where, in languages like Java or, never mind Python, whether you're working with a reference to an object or working in a scope where the object itself has been allocated, you're going to uniformly use dot. The C compiler will happily tell you that you used the wrong operator and failed to compile your code, so you can go and fix it. Now, and the last thing here is in other languages, you might have implicit or explicit object creation. C has the new C++ has the new operator to create a new instance of a type. In C, you've got malloc. Malloc allocates memory. It doesn't allocate objects or anything high level. If you call malloc 5, it will return a pointer to, it will allocate a 5-byte block of memory and return it to you. Clearly, if you want to allocate memory for a new object of type struct ABC, you'd better ask malloc for the right number of bytes, which is size of struct ABC. Yes?
So when you run malloc, does it return the address of the memory you allocated?
Yes. Yes. And then there's And then later, and there's no destructors. Eventually, you're probably going to want to call free on this pointer to return it back to the allocator, unless you have a simple program that allocates a bunch of memory and then exits. So basically, in fact, C makes a clear distinction between sort of three types of variables. So we've got global variables. Those are declared outside of any function. They're visible to any function as long as you don't define a local variable that shadows it. That's not unique to C. That's something you can do in just about any scoped language. There's local variables which are within a function. They can also be declared within smaller blocks within a function. In that case, their scope will be, the particular block that they're declared in. Just like other curly bracket based languages, to use a really technical term. And then finally, we have what are called heap variables, where so basically the compiler, the operating system, and the libraries that get linked with your code sort of define these three chunks of memory. There's the global variable region. That's as big or as small as all the global variables that your program declared, and all the ones that the libraries you used in your program declared and used. There's the stack. It turns out we're going to spend more time on it. It holds not just return addresses and function arguments. It also gets used to allocate local variables, which is great because every time, every time you call another function, you can allocate more memory on the stack just by subtracting, decreasing that stack pointer, and then you can free it when the function returns. So we'll see that in fact the stack provides a way to provide storage for variables that exactly follows the way that they're scoped, storage for local variables, that exactly follows the way they're scoped in the language. And then finally, the standard library maintains a big chunk of memory called the heap, and it allocates chunks of memory from that when you call malloc. And it returns them when you call free, and bashes them all together so that it can allocate them again in different sizes if necessary. We'll talk about how that's implemented in a few weeks, probably, in not too much detail. But the key thing is that these are memory allocations that live longer than a local variable in a function. That memory stays allocated until you free it again. If you're building a binary tree and you add a leaf node to it, or or a linked list, you're building a linked list and you want to append to it, you want to allocate a node to link onto that list that lasts longer than the append function. It's no use appending something to a list if the thing you appended disappears once you return from append. So, or worse yet, leaves pointers to something that's no longer being used, that's now being used for some different purpose. So structures like that are typically created by dynamically allocating memory using malloc, or using something that calls malloc at the very bottom. Obviously, any structure like that, we're going to, well, I guess one way to look at it is the other things we've talked about, local variables and global variables, are things that the compiler knows about. The compiler knows where this structure is located. It's in, the block of memory that was temporarily allocated on the stack for this function invocation. It knows where the 8 bytes of memory for this pointer was allocated. It knows where this global variable is, and it knows the names of these things. When a value gets returned from malloc, it's nameless. The compiler doesn't have a name for the result returned from malloc. It has, in this case, it has a name for the variable that we stick that result into. So we have a name P. We have a location. We have a location for P. And we have, a block of memory, which we will hopefully uniformly treat as a struct ABC, if we don't have any bugs in our program, which doesn't have a compiler assigned name. All we have is a pointer to it. So, for that linked list, for instance, we might have a local variable that points to it, and then we might return that pointer to another function. We might assign that pointer to a global variable, but somewhere we need a variable that the compiler can get its hands on that points to, that points to the memory that we allocated. or either directly or indirectly. If we've built up a tree, we just need a pointer to the root of the tree, or for a list, a pointer to the head of the list. Um, if we lose track of this memory, let's say we forgot to free p, and then we return from the function. Now we have no way to free that memory because we don't have any variables pointing to it, and we have a memory leak. It turns out there's some tools that, there's a number of tools that make programming in C somewhat more civilized, and one of them is a memory leak detector. This is something that's actually, it can be problematic in C++ as well, although the more modern versions of C++ have a whole bunch of things that if you use them and don't write C++ like it was 1995, then you're much less likely to have these leaks. Okay. Now, I haven't released Lab 1 yet, but I'll probably do it tonight after the 7 p.m. deadline that a couple of us have for a paper submission. And what I wanted to talk to you about today is, the C programming aspects of it. Because for most of you, it's going to be, your first real C programming, which is always a painful experience. So Lab 1 defines a simple 16-bit CPU, very similar to the one that I described on the blackboard. The difference is it doesn't have any hardware devices. It just has like an out instruction that sends a byte to the terminal and an in instruction that reads one. We need that so that we can write a hello world program, obviously. And so you're going to be writing an emulator for that CPU. So basically, okay, I'm going to use integer types from this particular header. They should be fairly self-explanatory. This type refers to an unsigned 8-bit integer. Yes? You do not. It's programming assignment. Let me call it programming assignment. It will go, it goes under, the breakdown showed 4 labs of 10 points each for a total of 40 points. If it doesn't say that, I'll fix it. Is that the old-fashioned website? It's Piazza? Oh, um, Canvas hallucinates syllabuses. It takes, so it sees that I created placeholder assignments that haven't been published yet for 10 homeworks and for 2 exams, and creates and hallucinates a syllabus based on that. If I add placeholders for the 4 labs, then that will fix things. But yes, that's one piece of advice: is don't trust anything. The only thing you can trust on Canvas is your own submissions and the grades for a particular assignment that I return to you. Because Canvas tries to calculate things, and its ability to calculate useful grade functions is very limited, especially the ones that it calculates without telling the instructor that it's doing so, and doesn't show up in one of my columns on the grade system. But okay, so this is a pointer to, so this type is just a byte. Don't even get me started on why we can't use the character type. There's some bizarreness in this in the C standard, and depending on the platform, this turns into character or unsigned character. Then it has an array of 8 registers. Those are all 16 bits. Arrays in C work pretty much like, pretty much like arrays in other languages. The only difference is that a lot of times it turns out that the name of the array is basically equivalent to a pointer to the beginning of the array. The compiler allocates enough memory for 8 copies of the type, and array indexing performs the math to select the the appropriate entry. Now, C is very stupid, so I can also do access way beyond the array, and it will try and read from some memory over here somewhere, which who knows what's there, or even if that might even be outside the program range and cause a crash. I can even do a negative index, and it will happily point to up here. Don't do either of these. In the case of our CPU, it's pretty hard to go outside the bounds of this register array, because in our instructions, the register is going to be indicated by a 3-bit field in the instruction somewhere. Once you extract that field, it's obviously going to be between 0 and 7. Okay. So this structure, I may be missing something, but um, this structure represents the state of the CPU, and you're going to write a function which executes a single instruction. It's going to read a 16-bit word from memory at, at the address specified by the program counter. It's going to perform whatever manipulation of these registers or possibly reading from or writing to this memory that's specified by that instruction. It'll update things, including the program counter, and then it'll return. Instructions are either 2 bytes or 4 bytes. The instruction encoding is 16 bits, and then some instructions have an additional 16-bit value tagged on. So most instructions will add 4 to this program counter when they're done, but jump instructions will set the program counter to something else. That's how you implement a goto. And the like I said, you'll write a function which executes a single instruction. That makes the test framework a lot simpler. It means I can give you a framework for running it that does things like verify that you change the program counter so it doesn't loop infinitely, and stuff like that. And so this writing that function is is going to require understanding all the instructions in the CPU and understanding the parts of the CPU that are represented in this structure. But the actual C code that you'll need to write is pretty simple and somewhat tedious. So actually, before I go on, let me ask questions about what I've covered so far, because I'm sure there's both the earlier stuff about structures and heap allocation, as well as this. Yes?
Yeah, what's going on in that code for the CPU? Do you feel like I'm out?
In which code? This? No, this. Oh, this is declaring a structure. So there's a pointer that's 8 bytes. There's 8 2-byte integers. That's another 16 bytes. There's another couple of 2-byte integers. That's another 4 bytes. And then these, I forget how whether the compiler allocates 1 byte or 4 bytes for each of them. So this declares a block of memory. That I think I got those reversed. It tells the compiler that this is what a struct CPU looks like. Yes?
What is the memory pointer for?
That's going to be for the RAM, the memory for our emulated CPU. It'll have 64K, 2 to the 16th bytes of memory. I suppose I could have had it just be I could have done this instead and made a structure that was a whole bunch bigger. Right now, it's always going to look like this, where we've allocated a block of memory for, we've allocated 64K bytes for the memory, and we've allocated, a few dozen bytes for the rest of the CPU.
So does it point to the whole of the RAM or like a specific instruction?
It points to 64K bytes, and those represent the bytes in our emulated computer. So if we execute an instruction that says store this byte to address 1000, we're going to use array indexing to store to the 1000th byte in this. We'll treat it as an array of bytes, and we'll store that value in the 1000th byte in that array.
So how would the code look like for that? Would it be like the pointer and then use arrow and index?
You know what? For today, let me do this, because that will that will yeah. In fact, I may change this in the lab and just test it quickly tonight. That will actually make one of the testing things a tiny bit easier. But I'm realizing too that the way you learn to think about writing C, after many years, you sort of internalize a bunch of things that are not the easiest way to explain things. So let's just make this an array here. And so it's very clear that this is actually struct CPU plus RAM. This is the entire memory of the computer, and this is all of its registers. Now, in your program, this lives in memory, and these parts of it have different addresses. And when you're writing C code, you almost never care what the actual addresses are. You never see them, unless maybe you're writing hardware drivers. Like I talked about the frame buffer having a fixed address on some computers or things like that. Instead, we won't be calculating addresses of the bytes holding this data. Instead, indexes into this array represent addresses in our emulated, CPU. The entire CPU lives inside C. It's a C program that just simulates what that CPU would do. Okay, so each instruction that gets fetched from memory, like I said, is a 16-bit word. It breaks down into a set of bit fields. And this is, pretty much how almost all CPU instruction sets work. Okay, let's see. Okay. Yes. 12 bits here and 4 bits here. This is so there's a 3-bit operation. A 3-bit operation field. So there's the first 4 bits, the most significant 4 bits in our instruction format for our pretend CPU indicate what instruction to execute. So, for this, we're going to be doing a lot of checking specific bits in a word and extracting them. And for that, we'll use the following, a number of math operators that we don't normally use. So first, we want to check the top 4 bits. And so we can mask off all the other bits by ANDing the instruction with a word that has 1s for those top 4 bits and 0s for everything else. I don't know. I think, and so this lets us make sort of the top level of our function be something like, so we can just do a bunch of if instructions and say, if instruction ANDed with the top 4 bits is all 0, then we do something. In fact, if I recall, the all zeros operation code isn't used, so we don't have to actually do anything here because, so one thing about this assignment, and actually the other labs in the class, I will tell you how your code is going to get used, and you won't be tested on, cases outside of that. So for this programming assignment, you will be tested on valid instructions. You won't be given illegal instructions. If you were writing something real, you'd have to handle whatever garbage got loaded. If the code accidentally jumped into the middle of a string and loaded nonsense instructions, you'd want it to do whatever the CPU definition says it does when it gets an illegal instruction, not just crash on you. I'm not going to do that, so you only need to worry about the legal instructions. So, somewhere so in this list, we're going to have this is the digit 5, no, that's the digit 6, 4 plus 2. So okay, now, so there's a switch construct that seems, that if they had done it differently would be cleaner than using a lot of if-elses, but they didn't. So unless you're familiar with C, I would suggest just do if it equals this, else if it equals that, else if it equals that, and then at the end, else, that's an error. Part of the problem with C is that the early compilers were very primitive and just, did were only like a level above machine language, and the odd behavior that they guaranteed got baked into the standard, and we're stuck with it today, which is why I'm not going to describe the switch statement.
So, does the ALU, is all of this defined when we define our struct in the lab? So when we define the CPU?
No, these operations, this is defined in a PDF file. You read this, and it has a box with, that looks like this on it, saying that, the ALU operations, add, subtract, and so on, have this format. They'll begin with these 4 bits and have these fields in it, and you have to pull the fields out.
This is an example like question, would it be? That we have to use our computer that we define?
No, you are writing code to simulate the toy computer. So this is an instruction for the toy computer. And so you'll be writing a function which executes a single instruction, pulls it from the memory, cracks it apart like this, and updates the CPU state. And then if we call that function repetitively, each time it gets called, your toy CPU will execute a single instruction. And I've only written 1 or 2 tiny programs for the toy CPU. You'll get assembler and a binary for a hello.world program that has a little loop that, obviously loads 1 character at a time into a register from memory and then outputs it and prints hello world. Yes?
Could you explain the point of the mask and all that?
Okay. That description says that, basically it says we've got this Um, I forget what they are, but this is totally wrong, but that the first thing you have to do basically to emulate the CPU, you're going to have to look at the instruction word and figure out what type of instruction it is, and then do it. So essentially, there's a machine encoding of each instruction. Because yes, you've got assembly language. It says, things like add this register to that register and store the result in this other register. The CPU doesn't read strings. It reads, this CPU reads 16-bit instructions. I've got a Mac with Apple Silicon that reads 32-bit instructions, with interspersed with 64-bit values and stuff. And and those instructions, if you looked up the if you looked at the manuals for those CPUs, which I don't really recommend, the Intel manual, you can get it in paper form and it takes up about this much shelf space. But, they will have, pictures like this saying this is how all of the, for instance, 1,000 instructions in recent Intel CPUs are encoded. We've got a toy CPU with 15 different instructions, or it's got more instructions than that because some of these instruction codes refer to like a family of instructions. So in this case, you know what? Okay, there's some acronyms that you see for so many years that you forget, that nobody knows. Has anyone heard the term ALU before? Okay, about 2 or 3 more than I expected. When you see a picture of a CPU, a diagram of a CPU, often they have something in the middle like this, an arithmetic and logic unit that takes, 2 values and produces an output. And has some controls on the side telling it which operation to perform on those 2. So anyway, I apologize for the acronym. This is basically all the math. This code, or whatever the correct one is the instruction code for all the math instructions, including the weird ones like bitwise and. Because the compiler would never be able to generate this code, or would have a great deal of difficulty doing so, if the CPUs on our machines didn't have a bitwise and operation in their CPUs. Oops. So the left shift up, sorry. Sorry, the right shift operator. Getting my left and right mixed up. The right shift operator shifts the bits in the word to the right, which means it dumps some of them off of the bottom, and it shifts zeros in at the top because you've got to fill that space with something. And so here, if we shifted x by 2, then instead of 1, 0, 1, 1, blah, 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 you get 0, 0, and then 1, 0. So basically, we were taking this and moving it down by 2 and filling the top with zeros. And I should have drawn it bigger. So, here we're just shifting all the bits down by 2. It turns out that right shift is the same thing as dividing by a power of 2. So right shifting by 1 is dividing by 2. Right shifting by 2 is dividing by 4. So, things like, there's some on, the toy CPU doesn't in fact have multiply and divide instructions like a lot of simple 8-bit CPUs. And so, if you wanted to implement a general purpose language like C, you'd need to write a library that that used shifts and adds and subtracts and so on to implement multiply and divide. Okay, now why was I talking about right shift? Because we'll want to get these fields out. So the operation we could do we could use the same approach to decode the actual operation. We don't have to shift anything around. We can just compare on these 3 bits. But for the registers, we want to get an actual index because we want to index into that register array. So okay, and then so going from binary to, working out a mask for something like this, um, sometimes it's easier or more reliable to just write out the binary bits and um, and then translate it into hex or something else that although I think I actually give these numbers somewhere in my in my instructions. So what this is going to do is it's going to mask the instruction with a word that only has these 3 bits set. So the result of this will only have these 3 bits, and then we're going to shift it right by 6. And the result is going to be something that looks like this. And now we've got an integer. We've got our 3 bits of A in the right place. And then for B, we're going to mask off everything except these 3 bits and shift it down by 3. And then for C, we just need to mask it with 7, which is just the bottom 3 bits, and 0 everything else out. And now we've got the 3 register numbers, and hopefully we can figure out how to use them to index into the register array. So if the instruction says, let's say it was add R1 plus R3 into R5, we would, basically we'd have a piece of code that said CPU our code would basically say assign, add R sub A, index by A to R index by B, and put the result into R index by C. And so after a number of lines of code breaking down the instruction into parts and getting all those different parts, the actual work that gets done is this line of code right here. It turns out emulating another CPU like this is pretty inefficient. You spend most of your time, like I said, picking things apart, figuring, pulling numbers out of different parts of the instruction and so on. It's much easier in the chip itself, where they just route each of these bits using wires to somewhere. These 3 bits go to somewhere that says, pick this register out of the 8 registers. But we don't have wires in C. We have masks and shifts and so on. Yes.
So with the instruction that RC, is that instruction RC, RA, RB?
No. If you remember, we had so this is the assembly language, and it gets translated into a 16-bit, machine instruction. Our code is going to read that machine instruction from the memory, do a bunch of work to figure out, oh, this is an arithmetic and this is a math instruction. The operation code is for an add. So let's get the A, B, and C fields out of that instruction. And now this is the actual code. This is the real guts of your implementation of that emulated function. Because what is this instruction supposed to do? It's supposed to add register A plus register B and put the result in register C. And if this CPU pointer points to our structure, then that's what this line of code is doing. It's adding the emulated register A, where A is between 0 and 7, to register B and putting it in register C.
So in the code, you isolate each ABC and get rid of the add instruction by masking, right?
Yes, I pull each field out by masking everything else and then shifting it down to the bottom. So when I'm extracting A, I have to extract the part that says add. I have to mask off the part that says add, the part that says that it's a math instruction, and these other parts. Well,
And
they're going to
is
get shifted off.
ABC a value or is it a address?
It's a register number. Each of this is a 3-bit register number. This is a 3-bit register number, and this is each.
And then what command do you put to go to that register? Or you do read and then
No, let's see. I think it's easy what I'm talking here. I wish I had 2 colors of chalk or something. I've got whiteboard markers, but that's not going to do much good. So it would be good to distinguish what are the instructions and code for the fake machine and what's going on in the real machine. So what's going on in the real machine is the C code that we wrote. And so that C code read a 16-bit value from memory, from the fake memory array, and it cracked it apart to say it's a math instruction, it's an add instruction, and that add instruction, and we know from the document that add instruction has 3 register numbers in it. And so we use ands and shifts to pull those 3 register numbers out. And then after all that work, we've got this one line of code which basically does the instruction on the fake CPU. It adds 2 registers and puts the result in a third. And yes.
Can you remind me the steps of shifting by however many bits and taking it and extracting whatever information you wanted from it? Like what? Remind me how shifting helps us reach our goal.
Okay. Because we could just use an and isolate these 3 bits, but they wouldn't be useful for our purpose because a 0, if they're all 0, it would be 0. If the bottom bit was a 1, the number would be 64. If it was 1, 0, it would be 128. We want values from 0 to 7. That's why we have to shift it all the way down to the bottom.
Gotcha.
Yes?
Is this the instruction format that we're going to use for every instruction code, or is this just the format for the
The ALU is the only one that has 3 registers, but it would be cruel to use a different format. So I didn't. So there'll be other instructions where you're extracting a register B and a register A. And honestly, I don't remember whether the documentation labels them ABC or ABC. The PDF that comes with the lab is definitive. The chalkboard is not. The last thing is the bitwise AND has weird precedence. You know how like times is higher preference than add and so on, that if you have A times B plus C, it's going to multiply the 2 and then add. Well, and is nasty. It's much lower preference than you would think, and so you always want to, in general, you always want to use parentheses, but especially when you're using bitwise and, you'll never go wrong having too many parentheses. So that's so questions. All right, I wanted to spend 10 minutes on the command line. Well, no, I wanted to spend 30 minutes on the command line, but I can't. I'll cover it on Thursday. Yeah, and there's a last few things about C that I need to cover. But anyway. Yeah, it's a crappy piece. Okay, so one thing I would suggest, there's a couple of mentions of it on Piazza, and I think in the homework, short homework 1, is skimming through. There's a website, the Missing Semester or something like that. It's a January break course at MIT run by students. I don't agree with all of it, especially they're definitely Vim people. I use Emacs, although I've no longer try to get anyone else to. But it has a lot of stuff about, just how to make the computer behave. The way we teach you computer science is like, we never talk about sort of the mechanics of dealing with the computer. The equivalent of, if you had a car, no one, if it was a mystery as to how you went and got gas or how to lock the door or things like that. If someone taught you the driving, but you had no idea of all the other things around it, it would be a pain. Similarly, it's useful being able to, to manage your computer to do more than just press a button in Eclipse or Visual Studio or whatever. So let's see. So the thing about the Unix or Linux command line, and actually the command line on the Mac is pretty much identical. It's identical on Windows subsystem for Linux. It's fairly close with the DOS terminal on Windows, and I'm not even going to talk about PowerShell. But most commands are just programs. You type a command like ls, and what happens is the shell searches a standard set of directories, usually /bin/user/bin, and maybe a couple others, where bin stands for binary because they didn't have enough bytes back in the 70s or something. And related to which is the fact that most Unix commands are given names that are either chosen by, you know, random draw from a Scrabble, you know, bag of Scrabble tiles, or at best are horrendously abbreviated. So that ls will list files. The ls-l will list files, you know, with will give you a long listing that tells you their size and, you know, owner and things like that. LH will give you the size in a human readable format. There's a few other options, but those are like the most useful ones. So grep, I have no idea what it stands for, searches for a pattern. It follows sort of a standard Unix, you know, pattern where you either give it a list, you know, one or more file names to search, or you can, or it will search its standard input if it's not given a file argument. Now, there's the you can create a pipe, which in this case the shell will spawn two separate processes. It will run ls and then take the output of ls and provide it as the input of grep. So this is a fairly useless command. It just lists all the files and then prints out only those files that have the string ABC in the name. It turns out we could have just done but there's a lot of other cases where we could use this. And so it's 1:23, so I'm going to stop now, and I will talk a fair amount more about the shell on Thursday.
I'm gonna harass you for like 5 minutes.
Okay.